In this video lesson, we talk a little bit about robot kinematics, trajectory planning, and control. As I mentioned in the introductory video, these topics are a bit outside of embedded design, but it's a fun subject, and we do need some of this to implement the draw module in the next lesson. So here's an outline which I'll go through briefly. We start with an introduction to robot kinematics. Then we'll do the kinematics of a planar two-link arm robot. Then we'll talk about trajectory planning and robot control. And then I'll present some prompts and give you my take on them. And finally, a lesson summary. Now, some of these items are very big fields of study, such as kinematics. So I'm just giving you a tiny taste of what it is about. But we'll be using some of this material in the next lesson. So what is robot kinematics? Well, it's the study of the movement of robotic systems. For example, for industrial robot arms, we're interested in the relationship between joint angles and the endpoint or tool point position. For steerable robotic cars, we're interested in the relationship between drive wheel rotations and steering angles and so forth to the car position. Now, the kinematic problems for these two types of robots I just mentioned are going to be quite different. The focus here is on robotic arms, since our demo project is a robotic arm. So two fundamental problems in kinematics are the so-called forward problem and the inverse problem, and we'll be doing both of these for our project. So before I continue, I just want to define the term tool point. On a robotic arm, the tool point is some defined location, normally at the end of the arm, and it might be the middle of a gripper or the point on a spot welder where the electrodes meet. For the course project, it's the tip of the pen. So the forward kinematics problem is this. Given the robotic arm joint angles, what is the position and orientation of the tool point? And another part of that is, what is the workspace of the robot? In other words, what positions and orientations can it achieve for the tool point? Now, inverse kinematics is this. Given a desired position and orientation of the tool point, what should be the joint angles? And I mentioned orientation of the tool point here, but as you'll see for our planar robot, we can't control the orientation of the tool point. It's always pointing downward. And that makes it a little bit simpler. So those are the problems we need to solve to control a robot. And the thing I want to mention, of course, as you might imagine, this is highly mathematical. There's geometry and trigonometry and all sorts of things involved in this. And beyond that, there are other mathematical difficulties. The kinematics equations can become quite complex and difficult to solve. Another problem is the inverse kinematics may have multiple solutions, meaning that to put the tool point at a certain location, there's actually different ways you can achieve that with different joint angles. And another problem is the inverse kinematics problem can be difficult to solve mathematically. In many cases, we say it doesn't have a closed form solution. You can't just calculate it like an equation. You have to use other mathematical techniques to find the solution. We won't be dealing with these difficult mathematical problems, but I just wanted to mention that is certainly a big part of kinematics, is the numerical calculations. So now let's look at the kinematics of a planar two-link robotic arm. This matches exactly the drawing machine that I built and I'm going to demo. And that's the main reason I chose it as an example, because we're going to need this stuff. But also, you'll see this problem in nearly all introductory kinematics textbooks because the equations are not too difficult to derive, but we still have some interesting results like multiple solutions. So if we look at this diagram, we see this robotic arm, and it's on a Cartesian plane with x and y axes. And here is the tool point of the arm, and we assume we want to use x and y coordinates to represent positions of the tool point. You'll also notice we derive joint angles, theta 1 and theta 2, and we use L1 and L2 as the lengths of the links. So this picture on the right just makes it clear that theta 2 is negative when the second link is in this position. So I'm just going to give you the results here, but if you Google this, you can find the derivations. I'll just warn you that there are different ways of expressing the results, so you might see different equations, particularly for the inverse solution. But of course, the equations might look different, but they're mathematically equivalent. So here is the forward kinematics problem where we are given the angles and we want to calculate the x and y coordinates of the tool point. And so this isn't too bad. The inverse solution is more complicated, but it still isn't too bad. It has a what we call a closed form solution, meaning we can just plug numbers into equations and get the answers directly. Now, the way this solution is expressed is to first calculate these three values, alpha, beta, and gamma. And then we, to get the joint angles, we choose one of these sets of equations and we plug in alpha, beta, and gamma, and pi in this case is just the constant pi. And that gives us the angles. Now, why are there two sets of equations? Well, in general, there are two solutions to this problem, and we call them elbow down and elbow up. And in fact, these two pictures try to represent this. I think you can imagine that if you have a point here, this joint here could either be down in this down position or it can be in this up position. And those are the two solutions. Well, we talked about kinematics, so now it's time to talk about trajectory planning, which you can think of as the next layer up. What I want to do on this slide is just introduce some of the topics in trajectory planning. I'll be using the planar 2-link arm as an example, so I can make things a little bit more concrete. So what trajectory planning means is calculating precisely how to move the joints to obtain the desired position, orientation, and speed. Of course, kinematics is a big part of this. So first I'll mention two types of motion at a high level. The first is simple point-to-point motion, which I think is pretty obvious. The second type is moving along a path, where the path is defined by a number of what we call via points and an endpoint. So you say, I want to move to some endpoint, but I want to go through these via points along the way. You could use the path method when it is important exactly how you get to the endpoint. For example, say the robot is reaching into a machine to pull out a part. As it reaches into that machine, it has to avoid parts of the machinery, and those you would do that using via points. Now the other thing is there's a concept of moving in joint space versus Cartesian space. Now the term space as I use it here is a mathematical concept, so I wouldn't try to equate it too much with the common view of space. Just think of a space as a collection of things that can be viewed as points. So let's talk about these two spaces. A point in joint space consists of the angles of all the joints. So for the 2-link arm we looked at, a point in joint space would be the theta 1 and theta 2 values. A point-to-point motion in joint space is just a move from an initial set of joint angles to a final set of joint angles. And for a linear move in joint space, all the joints rotate proportionally and in unison from the initial point angles to the final point angles. Now, movement in joint space is the most direct from a motor viewpoint, but it might not appear to you in your perception as a linear move, and the path might be surprising. And the reason is that the path of the tooltip is not a consideration in this kind of move. Now let's look at Cartesian space. A point in Cartesian space consists of distances of the tool point along the axes. So for the demo robot, that is the x and y coordinates of the tool point. For a linear move in Cartesian space, the joints are moved in such a way that the x and y coordinates of the tool point move proportionally and in unison from the initial coordinates to the final coordinates. When we are moving linearly in Cartesian space, the joint motions might be very irregular and at widely varying speeds, including reversing direction during the move. So here I show a diagram that shows the position of the tool point for a move in joint space versus a move in Cartesian space. And this diagram itself is on a Cartesian plane. So if we do a linear motion in joint space, this red line shows the position of the tool point. And you'll notice it does end and start and end at the right place, but in between it looks sort of like a curve and not what you'd think of as a linear motion. Now I actually just made up this curve, but this is typically what you'll see, and we'll check it out in the demo. But notice when we do a linear move in Cartesian space, which is the green line, it looks just like a line as you'd expect. And by the way, these black dots on this line, I'll discuss that in a little bit. By the way, in this discussion, I didn't discuss the tool point orientation. That's another job of trajectory planning, and it adds some complexity, but I won't discuss it here. So continuing on with trajectory planning and moving in joint in Cartesian space, trajectory planning for a linear point-to-point move in joint space is simpler because you just need to calculate the initial and final joint positions using inverse kinematics and then rotate each of the joints from the initial angle to the final angle. Of course, all joints must move in unison. Trajectory planning for a linear point-to-point move in Cartesian space is more complicated, and what is done is something like this. You compute a sequence of via points from the start point to the final point in Cartesian space. So you're breaking that path into a bunch of small segments separated by via points. And so in this diagram here on the screen line, these black dots represent via points. Then as motion proceeds, you convert the x and y coordinates of the next via point to joint angles, again using inverse kinematics. And then you move the joints in unison to the next via point. So a move in Cartesian space is really a sequence of small moves, each in joint space. So here are a few other trajectory planning topics. We've been focusing on position, but we also inherently control the speed of the joint or the joint tool movements during trajectory planning. And this includes doing things like smooth starts and smooth stops. And finally, path smoothing. All things being equal, you want smooth robot movements rather than jerky ones. So when moving along a path that is defined by a series of via points, you want the tool point to pass through those via points, but in a smooth way often. So there are various mathematical ways to take a set of via points and turn it into a smooth path. So the last topic in this lesson is robot control. So a robot controller can be viewed as part of a control system that takes the output from trajectory planning, which is joint positions and speeds over time, and aims to carry out those instructions. So for small robots with stepper motors, we have direct control over the joint speed and position. Of course, the motor torque required to move the robot as commanded must be within the stepper motor capabilities. For large robots using servo motors, traditional feedback mechanisms are used where the joint motor is driven electronically to minimize the difference or the error between the desired joint angle and the actual joint angle. And again, this is over time because the desired joint angle is constantly changing. Now, often the objective in these systems is maximize motion speed and minimize positional error. Of course, sometimes you can't have both and it's a bit of a compromise. And I also mentioned that sometimes position error at endpoints is more important than position errors that occur when moving between endpoints. So when the robot comes to a stop and is doing some precise operation, maybe picking up a part, position error there is important. Whereas when it then swings around, maybe it has picked up a part, it swings around, and it's going to put it down. During that swing around motion, maybe position error is not that critical. So here is a sort of a simple block diagram of a robotic system, as we've sort of been discussing. And so if we go from left to right, we start with motion planning, and that is the robot application program that's deciding what to do. And typically it outputs Cartesian coordinates of where the robot should be, and that's at a function of time. So that enters trajectory planning, and it then takes those instructions and it converts those, as you know, into the robot joint angles as a function of time. And that's theta 1 and theta 2. And then this theta 1, theta 2 prime, that prime is meant to represent a derivative. So these are the joint speeds. And those enter into the robot control, and its job is to take those values and make the joints do what trajectory planning is asking it to do. And that's through some kind of control signals. If it's a stepper, it would be the stepper patterns. Otherwise, it would be servo control. And in servo control, certainly you would have motor position feedback and maybe the velocity feedback as well. With stepper motors, of course, you don't necessarily have to have any feedback. So here are the prompts, and I'll just pause a second and then go through them. Suppose we enhanced our planar two-link robot with vertical motion to the tool point. How would this affect the kinematics equations? Well, there'd be a new joint variable, say z, which is the vertical distance of the tool point from a reference point. And we'll call it a joint even though it's a translational motion. This new joint variable would map directly to the Cartesian axis, again, perhaps with some offset. But because there is no coupling between the joint variable 0 or z and the other joint variables, the effect on the kinematics equations is small and it's simple. What is the effect of increasing the distance between via points when interpolating for linear motion in Cartesian space? Well, you'll lose path or position accuracy since between the via points you are moving in joint space, which in general is not a straight line in Cartesian space. What would happen if you tried to perform inverse kinematics on a point outside a robot's workspace? Well, you would either run into a mathematical problem or violate some constraint, such as a joint angle limit. For the planar two-link robot, let's assume L1 and L2 are 1. These are the lengths of the two links in the arm. In that case, the point 3, x equals 3, y is 0, is outside the reach of the robot arm, since that value 3 is greater than L1 plus L2. So this is definitely outside the workspace. So if you remember the inverse kinematics for that robot arm, you have to evaluate this term, this inverse cosine term. So if we try to do this and we plug in these values, then we get inverse cosine of 9/6. And 9/6 is greater than 1. You can't take an inverse cosine of a value greater than 1. It's not valid. And so that would be the result. In C, by the way, you would, if you try to take inverse cosine of that value, you'll get a value called not a number. So here's a summary of this lesson. We learned that robot kinematics allows us to convert robot joint angles to and from Cartesian x and y coordinates. we learned about trajectory planning and how it determines how to move the robot joints to obtain the desired position, orientation, and speed of the tool point. Robot motions in joint space have minimal joint movement, but the path of the tool point may be surprising. Robot motions in Cartesian space are performed by a series of very short moves, each of which is actually in joint space. Robot control takes the output of trajectory planning and makes it happen on the physical robot, often using feedback systems. Well, that's it for this lesson on robot kinematics and trajectory planning. Thanks for watching.